Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over double integrals over general regions. Well, what is a double integral over a general region? Pretty similar concept to the last video wherein we had a rectangular region where our x integral was bounded by a and b and our dy integral was bounded by our c and d. Well, this time we can just see it looks a little bit different here. Our region R, well, the y is now bounded by two functions, whereas the x is bounded by two constants now. So what does this mean? This means that instead of having just constants in our bounds, well, we're going to have functions now. And I guess that might have been a little bit intuitive, perhaps, but maybe I'm stating the obvious, but that's pretty much what over general regions is. That's what double integrals over general regions is. So say I wanted to find the volume of this 2D integral, this double integral, what am I going to do here? Well, the volume is going to be the integral from a to b, the integral from our lower bound to our upper bound of our f of xy, our integrand, dy dx. So how would I go about choosing my bounds, and how would I go about making a general region integral? Well, what I would do is procedurally, I would do exactly what I wrote down here. Well, I see that I have a general region on the bottom, I have a function on the top and a function on the bottom, What I'm pretty much just going to do is I'm going to draw a line from the bottom to the top. That's going to be my bounds. Well, starting from the bottom, that's going to be y is equal to g of x, therefore we have that right there. And we have the top being our y is equal to h of x being right there. Similarly, we're going to choose our x bounds, our dx bounds, left to right this time. So we're going from bottom to top for our dy and left to right for our dx. This may be counterintuitive to what we had learned in the past, seeing as, finding the area under a Calc 1 curve, when we did bottom to top, that was going to be dx, and from our y-axis to our whatever function would have been our dy. This might be counterintuitive. It certainly was to me at first, but this is just how it is, right? So we need to have our y is equal to some function in x and then differentiate that function in x so that we get that value, right? So that we get a value, we get a number instead of having that function like I was talking about earlier, wherein that's just not right. We're going to get the wrong answer if we do this wrong, right? So that's pretty much how we're going to solve the volume. Is our dy is going to be dictated by going from the bottom function to the top function, and our dx is going to be dictated by going from the left to the right. One of these is going to have to be a constant. One of these bounds is going to have to be a constant. So in this case, our dx is a constant. Like I said prior, that's what's going to give us a number. Similarly, we can have it the inverse way, wherein we have our x bounds dictated by functions. So similarly, like to the last one, well, what are we going to do here? Our inner integral is going to have to be those functions, right? So we're going to have our order now is going to be dx, dy. A little bit of a spoiler there. So how are we going to pick our bounds? Well, like I said, the procedure for picking our x bounds, we're just going to draw that little arrow from the left to the right function. So our lower bound is going to be where it starts. Well, like I said, it starts at that x is equal to g of y, ends at that x is equal to h of y. That's going to be our bounds. And our dy bounds, the exact same as last time. As you can see, I color coordinated here. It's going to be from the bottom to the top, so that's just going to be c to d. So our outer bound is going to have to be that c to d, because that's what's going to give us a number, like I said. Our inner bound is going to be that function in y. So just to kind of write it down there, our volume of this shape right here is going to be the integral from c to d, the integral from g of y to h of y of our integrand dx dy. Once again, this may be counterintuitive to what we're doing in Calc 1 and Calc 2, but I assure you that it will become apparent when we're doing our examples here why we are having our x in terms of y for our x differential and the inverse for our y differential. So I suppose one thing that I have to make clear now, we may want to switch our differential, and if we switch our differential, then we're going to have to redraw the region. So what am I trying to say here? I guess what I'm trying to say is when we have perhaps a function, well, in one order, it may be a little bit more difficult than the other. So therefore, if we just redraw the region, then change our bounds, switch our differential, then our bounds are going to have to change. It's not simple like it was in rectangular regions, wherein we were able to just flip it to constants. We were able to just switch one bound with the other bound. That's not something that we can do anymore, and I'm sure we can understand why that might be problematic. I guess I'm motivated by doing an example later on, perhaps a scary looking example at that, but I promise you, we'll get the idea of why we're going to want to switch that differential again, and why we're going to have to redraw that region whenever we're talking about general regions. So that's kind of the picture there. Those are the formulas on how we're going to do that. Well, let's go ahead and do our first example here. So we are asked to evaluate the double integral of xy over the region R, wherein our R is set notation over here of xy such that x squared is less than or equal to y is less than or equal to 2x. So we're given our region R, but it's kind of unclear on what we're going to do here. What are our bounds going to be? Well, we're given that region R, but it might be unclear to us right now what those bounds are going to look like, how we're going to translate our set notation into our bounds. Well, let's just go ahead and think about it. We're essentially going to split this up into two different functions here. So we have x squared is less than or equal to y, meaning what? Well, we're just going to go ahead and have a function there, right? Well, our function is just going to be y is equal to x squared. And similarly, we're going to have another function wherein we have y is less than or equal to 2x, meaning we are going to be taking, I'll explain that in a little bit, but we're going to have y is equal to 2x there. And like I said, you can see where I drove that from. We have those two right there. Well, we have y is equal to x squared, and then we have y is equal to 2x from that portion right there. So we have our region's functions there. Well, let's just go ahead and draw the region. Starting off with our y is equal to x squared, well, we know what that looks like. I'm only going to do it in the first quadrant because, well, that's what it's bounded by. I mean, I guess maybe I should have drawn this differently, but I guess I kind of cheated by knowing how to draw this prior. But we're going to be drawing this region. So this is going to be roughly around y is equal to 2x. I apologize, this is not the greatest photo. Well, I guess it would technically be kind of like that. We're not looking for accuracy. We're getting the idea across here. That's going to be our y is equal to 2x. And then our x squared region, well, what is that going to be? Y is equal to x squared. We know exactly what that looks like. I'm only going to draw the right half of it. Oops. There we go. Maybe I can make that. I don't mind that. You know what? I don't mind that. Y is equal to x squared there. Well, how are we gonna choose exactly what our bounds are here? How are we gonna choose what we're integrating over? Well, we can just see that these two functions, they create a closed shape, so it's pretty intuitive what that R region is gonna look like. So this is what our region over here is gonna look like. This is our region R. So we drew this. That's going to be the first step whenever you're doing these double integrals over general regions realistically. Perhaps I'll go over in the end and just make it clear that there could perhaps be conceptually a procedure to this. But I think generally we kind of understand now that we're going to just want to start off with drawing a photo whenever we're doing these. So we're drawing a photo here. Y is equal to x squared. And y is equal to 2x. We did our graph, so we have our region R. So now to find our bounds, well, let's just go ahead and restate this. Right here we have our region, our double integral over the region R of our integrand. Okay, well, let's look. What order here is going to be the easiest? Well, to be honest here, they're going to be pretty equally easy. If you want my opinion, I think they're going to be around equally easy. I think the standard order is going to be dy dx, and then when we get later on, I'll save that for later. But standard order here, what we're usually going to want to do is we're going to have dy dx. And let me check my color coordination here. My dy was, got rid of that color. It's okay. It's okay. Dy meaning what? Well, we're going to draw that arrow from the bottom function to the top function. So let's just go ahead and do that. Like I said, either order will probably be about equally easy. They're going to have different integrands, or they're going to have different bounds for sure. And swap differentials, but realistically, I think just looking at this, it would be about equally, but we're just going to go the kind of normal route there for our differential dy dx. So that's our dy. Well, what's our bottom function here? Our bottom function, it looks like, well, that's just going to be our x squared. And our top function is going to be 2x, meaning our bottom bound, our lower bound is going to be that x squared, and our upper bound is going to be that 2x. So let's just go ahead and do our integral. We'll make it long, because, I don't know, we'll just do that. I like my integral signs looking like that, I guess. Lower bound is going to be x squared. We're going to want those functions on the inner bound, or on the inner integral. X squared and 2x are right there. Let me rewrite my integrand right there, dy, or xy, and then we are going to be integrating in the order of dy dx. Well, we have to see here, what are our bounds on x? So it might be unclear here. Can't really draw an arrow like that, because then that's going to trip us up, right? That's going to be like, well, then we're going from 2x to x squared. That's not necessarily how we want to think of it. Well, what we want to think of it is, what's the range of our x values here within our closed region? Well, we have 0 right there. That's when they meet up. And what is this value up here? Where are these two equal? There we go. Well, where are these two equal? We're going to have to solve for this. So we have our y is equal to 2x and y is equal to x squared. Well, what x value are our y's equal? We're just going to set our functions equal to each other. So we're going to have 2x is equal to x squared. Let's label this x bounds. 2x is equal to x squared. Well, how are we going to do this? We're just going to subtract 2x. X squared minus 2x. Let's factor that x out. X times x minus 2 is equal to 0. So x is equal to 0. And x is equal to 2. So we see here now that this point right here is 2. And this point right here is 0. X is equal to 2 and x is equal to 0. So therefore, that's going to be our bounds on our x integral. We set up our integral. So now let's go ahead and evaluate it. Integral from 0 to 2. Integrating in terms of y, of xy, well, we did this last time. We have 1/2 xy squared from y is equal to x squared, and y is equal to 2x, I think, 2x dx. So now we are just going to plug that in. I'm going to pull, actually, no, I'm not. 1/2 x times 2x squared minus 1/2 x times x squared squared dx. Using fundamental theorem of calculus here, plugging that into there. Let's go ahead and, forgot my bounds. Let's go ahead and simplify this a little bit here. We're going to have integral from 0 to 2 of 1/2 x times, that's going to be 4x squared. 4 4x squared times x, that's going to be 4x cubed. So we're going to have 1/2 times 4x cubed minus 1/2 times x squared squared is going to be x to the 4th. X is going to be x times x to the 4th, x to the 5th. The x. I can simplify this just one little step further from 0 to 2. We're going to go ahead and cancel that out. We're going to have a 2 right there now. So our integral is 2x cubed minus 1/2 x to the 5th dx. Simple integral here, we're going to have, what is this, 1/2 x to the 4th minus 1/12 at x to the 6th from 0 to 2. Fundamental theorem of calculus, we have 1/2 2 to the 4th minus 1/12 2 to the 6th minus, well, if we plug in 0 there, there's going to be 0, that's going to be 0. Pretty simple there. Let's see. 2 to the 4th, 2 times 2 times 2 times 2, 4, 8, 16. That's going to be 16 divided by 2. That's going to be 8. We'll solve that later. 2 to the 6th is going to be 64. 64 divided by 12. 64 divided by 12 is going to be, well, that's not really going to be very pretty there. Do I want to calculate this? I might as well, I guess. 16 times 6, I got my handy calculator here because I don't feel like doing it in my head. It's 96 over 12 minus 64 over 12. That is going to be 32 over 12. Simplify that further. That is going to be, oh, what is that? That is 32 divided by 16 over 6, which is going to be divided by 2 again. That's going to be 8/3. That's our final answer. A little bit longer. Oh man, a little bit of a long problem there actually. Kind of overcomplicated the algebra perhaps, but I guess we're trying to get the concept here and not necessarily the algebra. I trust that you can do the algebra at this point. Yeah. So that was our first one. Second problem here. Got a star on it for a reason. Guess we'll figure out why in just 1 minute. We're asked to evaluate the double integral of 0 to root pi and y to root pi of sine of x squared dx dy. Well, let's just look at this. Can we, with our skills, do sine x squared dx? Can we integrate that? The answer is probably not. Maybe I'm speaking for you. Maybe some of you guys out there know how to integrate this just with your super skills there, but I personally don't. So what are we going to do here? Well, looks like we're going to have to switch the order. I can already tell you that right now. How are we going to switch that order? Well, in the past, we were just able to switch our bounds and switch our differential, and bang. That was going to be our integral. Unfortunately, this is no longer the case because of this y right here. This is a function, meaning we cannot do that anymore. This is what I'm trying to say here is when we're doing this, we have to redraw the region realistically unless the integral given is possible. So if this was given us in the dy dx order with the proper bounds, then this was definitely doable. We could do this. But unfortunately for right now, we cannot do this. We cannot do this with our integration skills as is. So what are we going to do? Well, what are these bounds saying exactly? Well, these bounds are saying that y in the lower bound, so our differential of x, that y is bounded with that pi, that square root of pi, right? So basically what I'm trying to say here, maybe I'm not verbalizing it very well, this x value is bounded from the lower by y and from the upper by the square root of pi. So basically what this is saying is that y is less than or equal to our x, which is less than or equal to the square root of pi. And perhaps that was more obvious whenever we were doing our set builder notation over there, is when we had that, well, we have y is equal to x, and x is equal to the square root of pi now. Oops, square root of pi. So similarly, we're going to do the same thing with our y function. Well, we're going to have 0 is less than or equal to y is less than or equal to the square root of pi, meaning y is equal to 0. And y is equal to the square root of pi. So how are we going to draw this now? Well, we know how to draw pretty much everything here, actually, conveniently enough. That y is equal to 0, well, that's just going to be straddling the x-axis right there. Y is equal to square root of pi. This is going to be kind of subjective. I'm just going to pop that right there. There's no scale here, but at least as long as we know what's going on. So this is y is equal to square root of pi. And this is y is equal to 0. And y is equal to x. We know what that looks like. That is going to be y is equal to x. And our x is equal to the square root of pi as well. So I guess the question here is, what are we looking for? Is this our region or is this our region? Is the question. Well, we can kind of just see that this right, I'll spoil it just a little bit and I'll explain why I know that, is this is going to be our region right here. We know that's going to be our region because y is less than or equal to x. This is really the key point right here. Well, y is less than or equal to x is meaning, well, we're going to be under that y is equal to x, right? We're going to be under that y is equal to x function, and that's pretty much the key right there, to be honest with you, is that's the key. So we have our region redefined. We redrew our region. So in one order, we had this order right now. Well, what was our current order? So for our dx dy, well, we had our y is equal to x going to our x is equal to the square root of pi. Well, we can't have that anymore. We just saw that that doesn't work. So we're going to have to write this in the dy dx version. So what are we going to be doing? We're going to be drawing our arrow from the bottom function to the top. And then we are going to be seeing, well, where does this go? Well, this goes from 0 to, what is this right here, square root of pi. So we just redrew our region there. We know what our new region is. We know our new bounds, and we know our new differential. And hopefully this makes it so that we can solve it. I guess we'll see right now. So our new integral is going to be the iterated integrals of our function, sine of x squared, dy dx. And what are our bounds on y? Well, we're going from y is equal to 0 to, what is that? Y is equal to x. So our bounds are now going to be from 0 to x. And our bounds on x are going to be going from, well, right here. Let me use my laser pointer. Right here to our square root of pi. So we're going to have 0 to the square root of pi. All right. At a glance, is this doable? Well, if we integrate this, then we're just going to pop an x or a y onto that sine x squared. That y is going to equal 0, that y is going to equal x, meaning, well, when we're doing our outer integral here, we're going to have x sine x squared. Well, that's a u sub right there, right? We can just do a u sub, so that's what we're going to do. This looks like it's doable now, right? So let's just go ahead and solve this integral. We're going to have the iterated integral from 0 to the square root of pi of this function, our integrand. Just skipping a step, I guess. Maybe not skipping a step. We're just going to plop that y in front. Sine of x squared. And our y is going to be going from 0 to x. Can't forget our dx outside. Now we're going from the integral of 0 to the square root of pi times, we'll plug that x in. That's going to be x sine of x squared minus 0 dx. Looking like I was right earlier. This is just going to be a simple u sub square root of pi x sine of x squared. We're going to let u equal x squared, and our du is going to equal 2x dx, meaning our new integral is going to be 1/2 0 to the square root of pi of 2x sine x squared dx. Rewriting that, we can just go ahead and write in 1/2 0 to the, we'll change our bounds. We'll change our bounds right now. What is that? Sine of u du. Our new bounds, we can switch it later. I'll just change them right now. Our new bounds is going to be, so that lower bound, well, when u is equal to 0, well, what is that going to equal? Well, then x is just going to be 0 again. Let me show my work. Well, when u is equal to, or x is equal to square root of pi, sorry, u is going to equal square root of pi, or yeah, pi squared, which is going to equal pi. So our upper bound is going to be pi, and then let me just show my work now. 0 squared is equal to 0. So these are our new bounds. Simple integration here. We have negative 1/2, sorry, cosine of u from u is equal to 0 to u is equal to pi. And we should know now we have negative 1/2 cosine of pi minus cosine, of 0. This is going to be negative 1/2 times cosine of pi is negative 1, cosine of 0 is 1, so we're going to have negative 1 minus 1, so this is going to be negative 1/2 times a negative 2, which is going to equal 1. So perhaps that was a good motivator for why we need to switch our differential again, but this time it wasn't so easy. This time we had to redraw our region, and we also just had to remake our bounds, right? So we had to change our bounds from 0 to the root pi to 0 to root pi again, actually conveniently enough, and then our inner bound went from y to root pi to 0 to x. So as you can see, I guess the main takeaway from our general regions is that when we switch our differential, when we want to switch our differential, or perhaps even when we need to switch our differential, we're going to have to redraw the region as well. Just in case. It's not always going to be easy as it was in rectangular regions. So that is how you do double integrals over general regions. Thank you.